Welcome to this lecture on application of rank to solve a system of non-homogeneous linear equations. All of us are familiar that this is one of the elementary problems in linear algebra, having wide applications in several fields of science and engineering. One can encounter such equations in control theory and circuit theory. A system of homogeneous, non-homogeneous equations appears like a11x1 plus a12x2 and so on equal to b1, and so on, am1x1 plus am2x2 and so on, amnxn is equal to bm. So this is an equation having m rows and n columns, or m equations involving n decision variables. Expressed in the matrix notation, it appears as ax is equal to b, where A is called the matrix of coefficients, x is the solution vector which we are seeking, and b is the constant vector on the right hand side. In order to investigate such systems, the process is a little bit more longer than working on a system of homogeneous equations. Here we'll have to determine the ranks not only of the coefficient matrix but also of the augmented matrix. An augmented matrix is a concatenation of the coefficient matrix and the constant vector on the right hand side. Now the system is inconsistent if the rank of the augmented matrix is greater than the rank of the coefficient matrix. If on the other hand, the ranks of these two matrices are equal, there are two possible scenarios. So either we can have a unique solution or we can have infinite solutions. Of course, infinite solutions have to be expressed in terms of free variables, about which we'll discuss. So the three scenarios are: when the rank of the coefficient matrix is not equal to the rank of the augmented matrix, we are led to an inconsistent system of equations in which we try to understand that there is no vector which will satisfy all the equations of the system simultaneously. So such a system is called an inconsistent system. We'll discuss about inconsistency in a very special situation at the end of this lecture without much details. The second scenario is when the rank of the coefficient matrix and the rank of the augmented matrix are matched. But when these common ranks is also equal to the number of decision variables, then not only is the system consistent for solutions, it produces exactly a unique solution. And the third scenario is when the rank of the coefficient matrix and the rank of the augmented matrix match, but this common rank is less than the number of decision variables. This leads to a system with infinite number of solutions, and such solutions are generally expressed in terms of free variables, and the number of such free variables is given by a number k determined by n minus the rank of the matrix. To explain these cases, let us take a few examples. This system of equations has got four decision variables x, y, z, and w, and embedded in four equations. So we take these four equations and then we first begin with the augmented matrix by combining or concatenating the coefficient matrix with the right hand side constant vector. So you know the right hand side constant vector elements are 9, 6, 3, and 2. So this is added at the fifth column to the coefficient matrix. So using elementary row transformations, we reduce this to its upper triangular form or echelon form. So the procedure of attaining the echelon form has been explained in this series of steps. And let us go to the last stage and see what we get. Now, when you look at this final output, it is a matrix having four non-zero rows in the echelon form. Now, This indicates that there are 4 linearly independent rows in the augmented matrix. So the rank of the augmented matrix is 4, whereas if you ignore the 5th column and only look at the coefficient matrix, its rank is 3, because to the extent of the coefficient matrix, there are only 3 linearly independent rows. Since the rank of A and the rank of the augmented matrix differ, therefore this system is inconsistent and has no solution. So as a very special case, we will see that even though the system is inconsistent, we can attempt an approximate solution to such problems, about which I'll make a brief reference at the end. The second example is an example where 3 independent variables or decision variables are embedded in 3 equations. And let us again start with the augmented matrix. This is a 3×4 augmented matrix. Using row operations, let us find out the rank of both A as well as AB. In this case, you'll find the rank of AB is 4 and the rank of A is also, the rank of AB is 3 as well as the rank of A is also 3. So they tally, and it's also equal to the number of decision variables. So the rank of A is 3, rank of AB is 3, and there are 3 decision variables. So therefore, this is a system which is not only consistent, it has a unique solution. So starting with the third row and writing 2z is equal to 2, we find z is equal to 1. Go one step up, build an equation, 2y plus 7z is equal to 12, and determine y. Go one more step, that is the first row, x minus y minus 2z is equal to minus 2, and back substitute y and z values, and you get x is equal to 5/2. So this is a problem which returns a unique solution vector. Now let us come to this last example, which is only of academic interest. So you can find in this problem that equation 3 has got 2 unknown values, A and B, A being the coefficient of Z and B is the element on the right hand side of the equation. Now the values of A and B have to be analyzed in 3 different scenarios. How will A and B behave when there is no solution for the system? How will A and B behave for a unique solution? And how A and B will behave in case of infinite solutions. So starting with the augmented matrix and using row operations, we arrive at a matrix which has been reduced to the echelon form, and then we take up each case separately. In the first case, when you have or when you desire that there should be no solution, the rank of A and rank of B should be different. So you fix the rank of A as 2 and the rank of AB as 3, and in such a case, A will be 8 and B cannot be 15. So when A is 8 and B not equal to 15, this system will not permit any solution. In the second case, when you want a unique solution, then the rank of A and the rank of AB should not only match, but it should also be equal to the number of decision variables. So you work out and then you will find that A minus 8 and B minus 15 should both be equal to 0, leading to A is equal to 8 and B is equal to 15. And then finally, we can discuss the last case when you have infinite solutions. And this is how we can use the concept of rank of a matrix to study non-homogeneous system of equations. Coming to the point that I was referring to, there are many times in scientific and engineering investigations that we may end up having more equations than the number of unknowns. And in such cases, there's a possibility that the system may not possess any solutions. In such a case, we can attempt trying to get an approximate solution to the system for which there are several techniques in linear algebra, and two of them, which are generally used to get approximate solutions in the least square sense, are the Moore-Penrose pseudo-inverse approach and also using the QR decomposition technique. Both these techniques will be discussed in the future lectures. So this is a brief lecture on how rank should be applied to discuss systems of non-homogeneous linear equations.